So, I want to go into the quote-unquote quote-unquote crisis in cosmology. And basically, I think it may be a similar case to general relativity and quantum mechanics not matching in their predictions of vacuum energy. They are both right for what they are measuring. I think that cosmic microwave background isn't fully understood, if I'm being honest, so that value probably still needs some tweaking, but it predicts the pure expansion of the universe and doesn't account for dark energy, just like general relativity. As such, it gets a lower value. So, what I'm saying with this part right here is that utilizing the cosmic microwave background radiation, right, to predict the expansion of the universe is one of the current methods, right? And so the value that you get for that is on the lower side of predictions. And the reason I think that is because it's not utilizing effects of dark energy, at least I don't think it is, in its calculations. And as a result, since dark energy is not being considered, your value is lower because, it's there, it exists, and it does have an impact. But it is not the core source, right? Just like in my other video where I was talking about this, general relativity sees, 0, but that's because it's not accounting for dark energy, whereas quantum mechanics is accounting dark energy, and so it gets an extremely high value, right? So that's why I think there's similarity between these things, where they're like, oh my gosh, what's going on? We're getting these wrong predictions, and it's just because each one is kind of missing parts, and so the predictions aren't exactly perfect. And what I said here is that I don't know if we necessarily totally understand what cosmic microwave background radiation is, so the value that we currently are predicting may need to be lower or higher. I'm not totally certain, based off of the proper understanding and the proper calculations and stuff. And I've talked about what I think I've talked about what I think it could be. Yeah, no, I've talked about it. Not saying that I'm right on that, but if I am, it would be cause to readjust what this prediction is, most likely. Observation, however, gets a predicted value that is higher. Or our method for measuring these distances could probably use some tweaking as well, as I don't think they are accurate at farther distances. So what I'm saying there is that another way that we observe this is we just look at other galaxies and stuff, or we utilize observations of different things, right, and we try and piece them together over time to see, okay, well, how fast are they moving away from us based off of the information that we're getting, right? And the way that we know that certain galaxies are the distance that they are away from us is by using, I don't remember it exactly, but it's something ladder or something like that, I think, where basically you use standard candles, I think is the term, which are these points where okay, we've confirmed the distance of this, and then you use that to judge the distance of the next thing, and then you use that, once you've confirmed that farther thing, to judge the distance of the next thing, right? And so we use that method to slowly figure out how far away everything is, right? But I think that the farther away you get, the less accurate that starts to become, and I don't think that our understanding of the universe is complete yet, and so I think that different factors might need to get applied to it that'll adjust it as well. What those factors are gets into, as I said in a video that I recently did with basically curvature of the universe and how that impacts stuff, and certain things we think are closer than they actually are might impact stuff. So not totally certain if these that calculation, that estimation is wrong, but I would assume that it might need some tweaking as well. That's why I think that I think our estimation is on the higher end when we are just observing it, right? Because basically we're overestimating certain aspects or underestimating certain aspects of what we're looking at. And so that causes a, fuzziness in our data and leads to a higher estimation than what it actually should be, maybe. I don't know. Regardless, this is because they are accounting for both the overall expansion and the addition that dark energy provides. I don't believe we are being pushed apart by dark energy so much as galaxies far from us are more likely to be attracted in another direction, and dark energy is just filling in the void. Either way, this would not be the same value for all galaxies at all distances, and so it would require some averaging of the data. I think that this is why we get a higher value than the more recent, potentially more accurate middle value. At further distances, this value of expansion should be higher, and I think that we just don't have the distance properly lined up. It makes more sense to me that the universe expansion is exponential in shape and isn't constant due to dark energy not being constant, and the whole distance thing. This may require the understanding that the universe is curved to make more sense, however. Basically what I'm saying there is that the only reason why I think that is probably because I see the universe as curved compared to most people, but the overall thing I'm getting at, why I'm saying it should be exponential, is because we know that dark energy is not constant, right? So it doesn't really make sense that when we, I was watching a video about this, and they show distance to galaxy, and the speed that they're moving away increases at a relatively steady pace compared to the distance they are away from us. And I don't think that it should be constant. I don't think that it makes sense for it to be a constant rate. And so I don't know if we just happened to pick data that made it look like that, or if our calculations are off, but I think it makes a lot more sense that since dark energy is not constant, this rate shouldn't be constant. And as we continue to expand outwards, right, things are going to continue to get farther and farther away at faster and faster rates, right? Because if you imagine moving out from a point, right, and then as you move away from each other like this, right, the distance you're going away from each other is increasing at a faster and faster rate, the longer that you are moving away from each other. And then on top of this, maybe the reason why we get a constant or an average that seems constant is because while this is happening, right, we also have mass condensing, right, due to dark energy. And so I don't think it's that dark energy is pushing things away from us. It's that things are getting pulled in by the flow of dark energy. And so as these are moving out, right, so if we imagine, right, everything's moving out, but some of these things are consolidating, and so as initially they were this far apart, but then they start to get even farther apart because they start moving closer to things that are closer to them. So instead of things being, constantly evenly spread out, they kind of consolidate. And so things get farther away than they initially were. But some things also get closer than they initially were, right? These ones were farther out and they came closer, right? So maybe that's why we get this seeming constant rate, even though I think that it really shouldn't be constant. But for every single thing, it should be a different value because it's not based just off of the initial motion, but also at this point now, after so much time has passed, all the motion of everything else around them plays such a heavy factor in this that, the collective whole is moving like this, but if you look at what's going on over here, they're moving all around, they're doing all kinds of stuff. So it's hard to tell exactly, it's hard to make any sense of it at this point, right? So I don't know. I think that the cosmological model should kind of basically consider both, okay, we have this initial expansion value, right? Which you would probably have to get by just kind of averaging everything and just hoping for the best. And then you would also then have to factor on some kind of additional value for dark energy. But the problem again is that some things will move closer because of dark energy, and other things are going to move farther away. So maybe it's better to just not think about the effects of dark energy at all, and have a correction factor of some kind for dark energy, like a factor, like a dark energy correction factor, to get a more accurate idea of the actual true expansion of the universe. Because really, dark matter is just throwing a wrench in the truth, because that's more of like that's not that's not, if we think about it from rest mass and then relative or like rest energy and relative energy. Our rest energy is the rate at which we're expanding outwards, right? And our relative energy is how we're moving around the mass that's around us, right? And that is basically the effects dark energy is having on us, right? So the effects of dark energy is the relative energy in this situation, and our rest energy is actually just what our constant expansion rate is, right? So that's our rest energy is moving in that direction, and our relative velocity only matters in comparison to the things around us and things away from us. But in reality, we're all like that motion doesn't matter, because we're all still expanding out at the same rate. And so in what to do with what I have just said here, that's a great question. I don't know. I think basically I think we could get a better estimate for what the expansion rate is if we just ignore dark matter, or not necessarily ignore it, because you can't ignore it because it's there, but if we put on some kind of factor of correction for it. So if we think that it's been it expanded by 25% because of dark energy, well then we put a correction factor on it that says like, okay, well maybe 3/4 of that is pulled away, as a bar of like within error bars, right? Like because we can never be sure. We can never be sure of what this is, because there's like the scales of gravity, like everything is within like another larger gravitational pull. So it's hard to know when dark energy is not playing an effect on this. So you can't really rule it out, and you can't really put a definitive, this is the value that we need to add. But I think we should try and add some kind of correction factor to help average and narrow down the value. Not that, honestly, I don't know if it really even matters to figure this out, because like, what does it change? I don't think it changes anything, so it's potentially just a pointless endeavor. But I guess if we wanted to get a better value, I think that's how we would do it. And I don't think that either one is completely wrong. I think is another point that I'm trying to make here. It's just that they're not using all the resources, or they don't have all the information, right? So really it's just a lack of information is why there's a discrepancy, is what I think. But yeah, so I don't know. Peace out.